Today we are going to continue with the topic on wave data analysis. Right now we will relate the wind data that we have to wave prediction. We're going to look at the SMB method developed by Swerdrup and Monk in 1947 and improved by Schneider in 1952 and 1958. The SMB method is a rigorous wave prediction procedure which involves a relatively simple wave energy growth concept with empirical calibration using small amount of data, which basically is the wind fetch, wind duration, and wind speed. We already discussed much about the wind duration and wind speed earlier. Wind fetch is defined as the distance that the wind has traveled over the surface of the water. So based on the SMB method, the significant wave height and the significant wave period basically is a function of the wind speed, the wind fetch, the wind duration, and G, which stands for the gravitational acceleration. So if we develop the non-dimensional terms from this correlation, we get these expressions here, which tells us that the dimensionless wave height and the dimensionless wave period is a function of the dimensionless fetch and the dimensionless wind duration. So what are these? Basically, instead of relating the individual variable, now we are relating them using the dimensionless term. This is the dimensionless wave height. You can see the significant wave height is in here. This is the dimensionless wave period. You can see the significant wave period is inside here. This is the dimensionless fetch or wind fetch, whereby F is here, and this is a dimensionless wind duration, whereby T sub D here represents the wind duration. By using the dimensionless term, it is much easier to represent the correlation so that the chart developed can be used, can be applied for wind and wave data from all around the world. Now we want to take note that the wave celerity C can be given by this expression, and we have another term called the wave age, which compares the wave celerity to the wind celerity or wind speed. This is the SMB wave prediction curves. On the horizontal axis here, we have the dimensionless wind fetch, which are plotted as solid curve, which is this one and this one here in the chart, and the horizontal axis here is also for the dimensionless wind duration, which is plotted as the dashed line here, which is this one and this one. So as we read the curves, we are going to be reading the value of dimensionless wave height. These two curves give us the dimensionless wave height. That means we can relate the wind fetch to the dimensionless wave height. We can also relate the wind duration to the dimensionless wave height. These two curves give us the dimensionless wave period. TS here is the significant wave period. So we can relate the dimensionless fetch to the wave period. We can also relate the dimensionless wind duration to the wave period. So there are a lot of information here, but basically we know that the wind fetch affects the wave height as well as the wave period. The wind duration also affect the wave height and the wave period. Let's look at this example. A deep lake has a wind with an average velocity of 30 meters per second, blowing over it for a period of 2 hours. The fetch in the direction of the wind is 20 kilometers. Using the Smb method, what significant wave height and period will be generated at the downwind end of the lake after 2 hours? Alright, so first and foremost, we are looking at a deep lake or a large lake, which is quite sizable, and obviously as wind blows on the surface of the lake, wave may also be generated, and we will have a certain wave period. So given the wind condition here, we want to find out what is the significant wave height and the significant wave period at the downwind end. That means at the other end of the lake after the wind has blown for 2 hours. Right, now we know that both the wind fetch and the wind duration affects the wave height and the wave period, as we discussed previously for the Smb method. So we are going to consider them separately. So this part we're going to consider the effect of wind fetch. This part we're going to consider the effect of wind duration. So for the given fetch, the fetch given to us is 20 kilometers. We first find out what is the dimensionless fetch. W is the wind speed is 30 meters per second. This is basically the fastest mile, although right now in the Smb method is represented using W. So this is the dimensionless wind fetch. So given this dimensionless wind fetch, we can go to the Smb chart. We read the value on the horizontal axis for the dimensional wind fetch. We can go to the solid curve, which is this one, and read across to get the dimensionless wave height, and what we get from the chart is 0.034. And based on that, since we already know W and we know G, we can then calculate the significant wave height, which is 3.1 meters. And likewise, for the same dimensionless wind fetch, we can read the other solid curve here to get the dimensionless wave period on the vertical axis. And this is the value that we get from the chart. Since we know G and W, we can use this to calculate the significant wave period, and we get 6.4 seconds. What it means here is that if the wind blows over the surface of this lake over a distance of 20 kilometers, we expect to get wave height, significant wave height of 3.1 meters and significant wave period of 6.4 seconds. But that is only based on the effect of fetch alone. Now let us consider the effect of wind duration. So first we work out the dimensionless wind duration. The duration is given as 2 hours. Okay, so we have 2 times 3,600 seconds. So we get the dimensionless value as 2,354. We go to the horizontal axis, and then we go up to the dash curve this time. We read across to get the dimensionless wave height and use that to calculate the significant wave height. We get 3.9 meter. Again, we repeat, we read to the next dash curve. We read across to get the dimensionless wave period, which is 0.4. We use that to calculate the significant wave period, get 7.7 seconds. Now, with that, we get the solution of the significant wave height and the significant wave period due to the effect of the wind duration. So now we have two solutions. Both depends on a different factor. This solution here depends on fetch. This solution here depends on wind duration. Now, the final solution should be the smaller value. Which means that the significant wave height can only reach up to 3.1 meter. Although the effect of wind duration might bring the wave height up to 3.9 meter, but right now the fetch is limited. The fetch only can allow it to grow up to 3.1 meter only. So the fetch has control how much the wave height can develop. So in the same way, we have two values of wave period. The smaller one will control, the smaller one will dictate. So we say that in this particular case, in this deep lake, the wind fetch is the limiting factor, such that for this condition given to us, the significant wave height and the significant wave period are expected to reach these values instead of these values. For the problem that we have just discussed, we say that the solution is fetch limited. So if we go back to look at the fetch, the wind fetch case, we notice that the dimensionless wave height and the dimensionless wave period are these two values. So if we go to the chart again, for this particular dimensionless wave height, if we read from the dimensionless wave height to the dash curve, and now grid downwards to obtain the value on this axis, we get the dimensionless wind duration to be this value. Likewise, we can do the same using the dimensionless wave period. From the value of the dimensionless wave period, we read across to the dash curve, and then we read downwards to obtain the dimensionless wind duration. So the value that we get should be approximately this value, which means that this will allow us to calculate the wind duration in seconds, and that is equivalent to about 1.5 hours. So in this particular case, it means that since the fetch is 20 kilometer and it is limiting, it is the limiting condition, the limiting factor. So although the wind blow for up to 2 hours, only the first 1.5 hours build the waves up to the significant wave height and the significant wave period that we have just calculated. The remaining half an hour, the condition on the surface of the lake has already reached an equilibrium. Although the wind continues to blow on it, although the duration is longer, but the wave height and the wave period cannot increase anymore due to the limited fetch. To summarize, the Smb method is applicable to deep water wave generation. For shallow water wave, we need to take note that when the wave grow with the wind speed and the wind duration and the wind fetch, they can quickly become limited by the water depth. So in order to consider the effect of the water depth on the shallow water bodies, the Smb method can be extended to include additional dimensionless terms that take into consideration average water depth. However, there are limited data available in this case, and so if we apply the Smb method on shallow water wave condition, we need to treat the results with caution.